All right. Welcome to class. So we have previously discussed and introduced our very short kind of lectures on unstable isotopes, and particularly unstable isotopes' journey to stability through radioactive decay and the emission of radiation, or the emission of a high energy particle. That's radiation. We talked about 3 out of like 7, 8, 9 types there are, because these 3 are the most common. Can anyone tell me what are the 3 types? Liam. Alpha, beta, gamma. Please make sure to know how to reference them via their Greek symbols as well. All right. Alpha looks like a fat fish, goldfish. Beta looks like a cutesy bee. And gamma looks like a upside down cancer awareness ribbon. Okay. So can you tell me a little bit about alpha and what particle is emitted? What is the type of high energy particle or radiation emitted from each? So let's see. Jennifer, could you tell me what alpha always emits? What's the particle that alpha decay always releases? What's the particle that alpha decay always releases? What does the particle it releases? What type of matter does it release? What's that high energy radiation it produces every time? So alpha decay always releases helium-4, or another way to write it is 4He2. Mass number on top. Okay. I see now that I do not have my screen sharing. So it can be written in 2 ways. Helium-4, this is called isotope name notation, or it could be written as 4,2 helium. This is particularly the method that we use when doing nuclear change equations. Like, this is how we show it in our nuclear change equations, is we highlight not only the mass number, the unique mass, which, by the way, is the definition of what an isotope is. It's a unique mass atom of an element. It's this particular mass quantity for a given element. Okay. And we could write it in 2 ways. One gives us all the information that we need, mass number and proton count, the identity. It's like the social security number of the element. And one just gives us the name and the mass. Both are valid. Both you should be able to read. Both you should know where to look on the periodic table for. Okay. So alpha releases helium-4. Okay. What do we know about alpha? Bryce, can you tell me what we know about alpha?
It's the least dangerous or the weakest.
Yeah, it's the least, like, if you had to be exposed to radiation, you'd want alpha radiation, right? Which is kind of ironic, because when we use alpha nowadays on a sociological term, we say, oh, he's an alpha, he's a beta. And I did hear that he's an omega is an even higher one, I heard from somebody. Okay. But this is the exact opposite here. Here it has nothing to do, alpha, beta, gamma has nothing to do with your social status or your, if radiation had a status. Okay. It has everything to do with the particle it releases. Okay. So out of all of them, alpha's, ideal. If we're being exposed to radiation is at all ideal. What's the second type of radiation, and what particle does it release? Valeria, what's the second type of radiation, and what particle does it release? You have notes. You got it. Beta, what does it release? Uh-huh. Say it more confidently. Yeah, well, an electron is negative. So it releases an electron. Exactly. It literally releases an electron. That is the high energy particle. That is the radiation. All right. It could be written as just an electron, or it could be written in the format of mass, which is, by the way, 0. We basically say an electron is 0 mass. -1, it's basically the opposite of a proton. So its proton count is -1, -1 charge. Electron. That's another way we could write it. All right. What do we know about beta particles? Diego? Okay, they travel 3 to 6 feet. What else do we know, Roman? Okay. What else do we know about them, Lily? Beta particles?
They travel at 3 to 6 feet.
Okay, what else do we know about them? What can they be stopped by?
They can be stopped by, no,
Yeah.
they can be stopped by steam.
Not really sure why neither of your notes were up.
Be stopped by water.
Mm.
They're like mid dangerous, they're like not,
Okay, what can they be stopped by?
they can be stopped by metal or a chunk of cement.
Okay, so a thin piece of metal or a chunk of cement. Okay. What about the last one? What do we know about the last one? What's the last type of radiation, Michaela? Gamma. Tell me a little bit more about gamma. Jose? And it's not really a particle. What is it actually? It is literally pure energy. It just releases energy. We write that as a 0 mass, 0 proton particle. We call that, by the way, a photon of light. A photon of energy is just a particle of pure energy. No actual mass to it, which is kind of anti, what you think. Tell me about gamma. Do we love it? Do we hate it? What do we think? Danny? Okay. Why is it so dangerous? Why fundamentally makes it so dangerous, Jocelyn? Okay, it'll basically travel forever and less stopped. What else makes it super dangerous? If radioactive decay is the process of an unstable isotope trying to become stable, why is it so dangerous? Yes.
Because there's no actual processing.
There's no actual transformation. Yeah, process of transformation or transformation. Your unstable isotope is not changing at all. Nothing. It's just emitting its toxic energy to you. Okay. So, then I talked about, good job, you guys. That was a good review. We talked about and looked at how do we write these nuclear transformations in an equation format with the unique format of including mass number and proton count. And we talked about one, the law of conservation of energy still applies, but here we're not balancing with coefficients. Now we're basically adding up. Okay. So if I have the alpha decay of plutonium-239, what this would mean is my unstable isotope, okay, plutonium-239. Now, for this format to work, what else do I have to include in this format? The proton number. So what is the proton number of plutonium-239 according to the periodic table? Plutonium. 94. Okay. If I write plutonium-239, do you look for 239 on the periodic table? No. Can you ever find a whole number, mass number on the periodic table? No. It's unique to an individual atom. Hence why we talk about it being an unstable isotope. Okay, isolated, not on the periodic table, isotope, and a one-of-a-kind atom of that element. Okay, then we say it undergoes alpha decay. If I say I'm doing alpha decay, what does that mean I'm always going to make then? Helium-4. So I automatically know one of my products is helium-4. Mass of 4, proton number, identity of 2 that I can find on the periodic table. And then how do I figure out what remains? How do I figure out the remaining theoretically more stable daughter isotope? What do I know must be true about the new atom? It must have a mass and a proton number that adds up to what? The original total. So, Carlos, what is the mass number and the proton number of my new element? Okay. So what is my element identity with the mass with a proton number of 92? Uranium. Okay. Uranium 235. So how would I describe this process? Which, by the way, is totally a question on a test where I have you do an alpha decay and then describe the process, FYI, is I would say unstable parent isotope plutonium 239 undergoes alpha decay, emitting an helium-4 particle. And English sucks with articles. Hold on. A helium-4 particle. And produces the more stable daughter isotope of the new element, uranium 235. As you can see, it's kind of nicer to write out the equation than it is to write out the process, but you should be able to, of course, be able to interpret what that equation is telling you. And it's very important that you label unstable versus stable. That matters. If everybody stayed unstable, then what's the point of this, right? You also should be able to identify what's the particle. We call any particle that's the radiation particle associated with a particular decay as the type of decay particle. So we would call this alpha particle. If I was emitting an electron, we would call that a beta particle. If I was emitting pure energy, we'd call that a gamma photon particle, okay? Where is the dangerous high energy source? It's your particle that you're releasing. It's your high energy particle that's the dangerous part, the radioactive part, okay? The part that rips through you. It's not the uranium that's the problem anymore, because that's theoretically stable. That should be fine, okay? So that's alpha decay honors. Whoa, God. You will be learning about beta and gamma and be tested on writing those, but they're really easy, okay? Some of you have already watched the video, right? One last thing I want to mention is this idea of what you guys are more familiar with, which is fusion and fission. They're actually separate categories of nuclear reactivity, because here it isn't really about decay. It's more about forced mushing together or forced ripping apart. Decay is pretty natural. Decay happens on its own, right? We know that by the concept of half-life. If you just give it enough time, it'll happen. This does not happen on its own. This has to be forced through like a giant, like as large of a city industrial warehouse, like simulator, and or, you know, for like other means, underground stuff, okay? That of course America doesn't have, right? Because America stopped producing nuclear weapons according to this contract we made with the world. Okay, so fission. Totally different type of nuclear reactivity. Like these are nuclear reactivity, not nuclear decay categories. Okay. Fission is the process of colliding. Oh, not colliding. Sorry. Splitting. Haha. Of splitting an atom. Okay. Which takes an immense amount of energy, but then produces an even larger one. All right. Fusion is the process, if you could not already tell, of colliding two atoms together. Both release immense amounts of energy. Even more energy than natural decay. Both require energy input, but the energy output is just at such a large scale, it negates any of the energy input. No. So, we will not be getting into fission and fusion. It is not a topic of concern right now. Though I will say is, if anyone knows the student Lila, she has actually worked on behalf of like nuclear conservation projects and organizations. And it is really interesting. Basically, nuclear energy and nuclear warfare, right, is the future of warfare other than digital warfare. It's going to be nuclear and digital. It's going to be a lot less kind of physical combat. It's going to be far more massive annihilation or digital control. So things to think about. But yeah. All right. So for the rest of the time, what you're going to do is honors. This is the time for you to finish up the video if you haven't already watched the 7-minute video. And then everybody else / everybody, you have stations of practice to go through to understand nuclear decay in preparation for understanding your project. So go ahead and take about 20 minutes to work through practice stations, finish up honor stuff, and talk to me if you need to. All right, guys, good job.